Okay, I'm about to walk through what I would categorize as fun problems, but um, many of you may see them as overly burdensome or difficult. But we will get through them. One of the problems that happens in this section is that we're taking two known things. We're taking eigenvectors, we're taking linear transformations, and we're mashing them all together. So realistically, there's not a whole lot of new content here, but the process feels a little bit unwieldy and a little bit foreign. So I'm going to walk through these step by step. The first two, not so bad. Problem number one, we have a statement here that we want to show that lambda equals 1 is an eigenvalue of e to the x over the given transformation. So the transformation here is the derivative, and we have shown to some extent that the derivative is a linear transformation, but we're asking you to kind of take our word for that. But this is actually a pretty straightforward problem, because if I take the transformation of the function e to the x, I get back e to the x, which means that the transformation of f is 1 times f, which means that 1, lambda equals 1, is an eigenvalue for this transformation. All right, so similarly, problem number 2 is not that challenging. If I take the same linear transformation of e to the 2x, right, I'm going to end up with negative 2e to the negative 2x, which means that the eigenvalue that corresponds to e to the negative 2x here is negative 2, because if I take t of f, this is the same thing as negative 2 times f, which means lambda equals negative 2 is an eigenvalue of t that corresponds to the eigenvector f. All right, so those two not so bad. When we get into problem number 3, this is where we start getting tripped up a bit. So we have the linear transformation t of a0 plus a1x plus a2x squared, not a2x2. Sorry about that. I'm going to pause for. All right, so that's a2x squared is giving me negative 3a1 plus 5a2 plus negative 4a0 plus 4a1 minus 10a2x plus, I can put it up here, 4a2x squared. All right, so what you're trying to do here is find a matrix, okay, that works with the coefficients. So I'm going to multiply this matrix times a0, a1, a2, and what I want to get back is the coefficients here, negative 3a1 plus 5a2, negative 4a0 plus 4a1 minus 10a2, and then just 4a2, right? So think about this way. If I do row by column, right, this row has to be 0, negative 3, 5, because that row by this column gets me this. The second row has to be negative 4, 4, negative 10, because this row by this column gets me that. And the third row has to be 0, 0, 4. This matrix is my crucial matrix, because this is the matrix I need the eigenvalues for. So what I do is I throw that matrix into MATLAB. 0, negative 3, 5, 4, 4, negative 10, 0, 0, 4, And MATLAB's going to throw me back a column vector, -2, 6, 4. I now have the 3 eigenvectors for this linear transformation. Lambda 1 is -2, lambda 2 is 6, lambda 3 is 4. Okay, so those are the 3 eigenvalues. Now, figuring out the eigenvectors takes a little bit more work. And what I'm going to do is I'm going to show you how to find the eigenvectors, and then I'm going to show some examples of why this works, because I think it's a little bit less than intuitive. All right, so let's work with the eigenvalue lambda. We'll call it lambda 1 is a -2. All right, if this is an eigenvalue, then I should be able to take -2 times the input 0a0 plus a1x plus a2x squared and get the output -3a1 plus 5a2 plus -4a0 plus 4a1 minus 10a2x plus 4a2x squared. Okay, so this can be broken into 3 equations. We get the constant term, right? -2a0 should equal -3a1 plus 5a2. The coefficients for the x term should line up. So a1, -2a1 should equal -4a0 plus 4a1 minus 10a2. And then a2 should line up with 4a2. Sorry, -2a2 should line up with 4a2. So, all right, let's put these into standard form. That's -2a0 plus 3a1 minus 5a2 is 0. 4a0 plus 2a1. Nope, that's not right. That's going to be -6. Plus 10a2 is equal to 0, and -6a2 is equal to 0. So this gets me a system of equations which is solvable by Gauss-Jordan. So I'm going to throw that into -2, 3, -5, 0, 4, -6, 10, 0, 0, 0, -6, 0. When I do Gauss-Jordan on this, I get back 1, -3 halves, 0, 0, 0, 1, 0, 0, 0, 0, 0. So that feels like a minus, or a0 minus 3 halves a1 is 0, and a sub 2 is 0, which means that a sub 0 is 3 halves some parameter, a sub 1 is some parameter, a sub 2 is 0. Okay, this means that the functions that are eigenvalues or eigenvectors for this are in the form 3 halves t plus t times x, and this will hold for all t's in the reals. Now, let's check this real quick. So the theory here is I pick some value of t. So like let's let t equal 2, because that way I get rid of that fraction. So I now have the function 3 plus 2x. All right, I'm going to take the linear transformation of that. When I apply the linear transformation here, I get -3 times 2. That's the constant term plus negative 4 times, sorry, it's not 3 plus 2x. That's not correct. No, it is 3 plus 2x. Yeah, that's going to give me negative 3 times 2, negative 4 times 3, plus 4 times 2 times x, plus 4 times 0 times x squared. This becomes negative 6. That's negative 12 plus 8, which is going to give me negative 12 plus 8 is negative 4. X, that goes to 0. So this is the same thing as negative 2 times 3 plus 2x, which is what I expect to happen. Is if my eigenvalue is negative 2, I should put the function in to the linear transformation, and all that linear transformation should do is multiply that function by negative 2, which is exactly what it did. Alright, so let's see if we could speed this up a little bit for the second eigenvalue, which is 6. Alright, so let's take lambda 2 is equal to 6. So we want 6 times the original function. And we should get back this, right? All right, so 6a sub 0 should be negative 3a1 plus 5a2. 6a1 should be negative 4a0 plus 4a1 minus 10a2. 6a2 should be 4a2. All right, putting that in standard form, 6a0 plus 3a1 minus 5a2 is 0. 4a0 plus 2a1 plus 10a2 should be 0, and 2a2 should be 0. Alright, so that gives me 6, 3, negative 5, 0, 4, 2, 10, 0, 0, 0, 2, 0. We do Gauss-Jordan, and we end up with 1, 1/2, 0, 0, 0, 1, 0, 0, 0, 0, 0. So a1 plus 1/2 a0 plus a1/2 a1 is 0, a2 is 0. So this means a0 is negative 1/2 t, a1 is going to be t, and a2 is 0. So the function that works here is going to be negative 1/2 t plus t times x for all t which are reals. Alright, so we can check again, right? Just kind of making this make sense. And again, it makes sense to let t equal 2. So we're going to take the transform. If I put 2 in here, I'm going to get negative 1 plus 2x. If I do that transformation, I should take negative 3 times 2. So that's my constant term. Negative 4 times negative 1 plus 4 times 2 times x is the linear term. 4 times 0 times x squared is the quadratic term. That comes out as negative 6 plus 12x, which is the same as 6 times negative 1 plus 2x, which is exactly what I should expect to have happen because my eigenvalue is 6. All right, so let's do the third eigenvalue for this problem, which is 4. All right, so again, we have lambda 3 is 4. So 4 times a0 plus a1x plus a2x squared should be negative 3a1 plus 5a2 plus negative 4a0 plus 4a1 minus 10a2x plus 4a2x squared, which means I get these equations. 4a0 should be negative 3a1 plus 5a2. 4a1 should be negative 4a0 plus 4a1 minus 10a2. 4a2 should equal 4a2. All right, so playing that out, I'm going to get 4a0 plus 3a1 minus 5a2 is 0. 4a0 plus 10a2 is 0, and 0 is 0. All right, so let's build the matrix. This is going to be 4, 3, negative 5, 0, 4, 0, 10, 0, 0, 0, 0, 0. We do Gauss-Jordan, and we get 0, 1, 0, 5 halves, 0, 0, 1, negative 5, 0, and zeros across the bottom. So this means a0 is plus 5 halves, a2 is 0, a1 minus 5a2 is 0, so a0 is negative 5 halves t, a1 should be 5t, and a2 should be t. So my function is going to be negative 5 halves t plus 5tx plus tx squared. All right, so this one's a little more complicated. Let's check this one, see if it works. Again, we're going to let t equal 2 because it's simple that way. So we're going to take the transformation of negative 5 plus 10x plus 2x squared, which is going to give me negative 3 times 10 plus 5 times 2 plus negative 4 times negative 5 plus 4 times 10 minus 10 times 2 x plus 4 times 2x squared, which works out to be negative 20 plus 40x plus 8x squared. Sorry, this should be a plus there. Plus 8x squared, which is exactly 4 times negative 5 plus 10x plus 2x squared, which is the expected result for the eigenvalue 4. All right, so there we go. That's problem number 3. Quite a bit of ground covered on that one. Let's look at number 4, which is very similar. Fortunately for us, it only has 2 eigenvalues, so let's take a look at that one. All right, so we're going to follow the same pattern in 4 as we did in 3. So the transform here takes something in standard form and gives us back 2a0 plus a1 minus a2 for the constant, plus negative a1 plus 2a2 for the linear, minus a2x squared for the quadratic. So what we're going to do is we're going to take eig of these 3 sets of coefficients, 2, 1, negative 1, 0, negative 1, 2, 0, 0, negative 1, which shouldn't be a surprise because this is diagonal. We have 2, negative 1, negative 1 are the eigenvalues. Aha. So, if you go back to, anyway, so if we're going to work with the first eigenvalue here, which is the 2. So let's do that first. All right, so lambda 1 is going to equal 2. So this means that we want 2a null plus 2a1 plus 2ax plus 2a2x squared to be the same as the transformation equation. 2a0 plus a1 minus a2 plus negative a1 plus 2a2x minus a2x squared. So 2a0 should be 2a0 plus a1 minus a2. 2a1 should be negative a1 plus 2a2. 2a2 should be negative a2. All right, so this means I get negative a1 plus a2 should be 0. 3a1 minus 2a2 should be 0. And 3a2 should be 0. Okay, so this is going to give me the augmented matrix 0, negative 1, 1, 0, 0, 3, negative 2, 0, 0, 0, 3, 0, which when I run that through Gauss-Jordan gives me 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, which tells me that a1 has to be 0, a2 has to be 0, and a0 is a free variable. We can write those in order. So this means that the eigenvector function is just t for all t. Reals, it's just a constant term. So let's check that. Let t equal something simple like 1. Then t of 1 is 2 times 1 plus 0, which is 2 times 1. So that checks. All right, and that will check for any constant value. So we have a second eigenvalue, which is negative 1. So let's try that. Okay, so lambda 2 is equal to negative 1. So we're going to multiply negative 1 by each of the original coefficients. And we're going to get 2a0 plus a1 minus a2 plus negative a1 plus 2a2x minus a2x squared. All right, so breaking that out, we're going to get negative a0 is 2a0 plus a1 minus a2. Negative a1 is negative a1 plus 2a2. And then negative a2 is negative a2. So this is going to yield 3a0, negative 3a0 minus a1 plus a2 is 0. The second one just becomes negative 2a2 is 0. And the last one becomes 0 equals 0. So we build the augmented matrix. Negative 3, negative 1, 1. 0, 0, negative 2, 0, and then all zeros. We run Gauss-Jordan on that, and we're left with 1, a third, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. So a0 should be plus a third a1 should be 0. a2 has to be 0. So we can look at this as a0 is negative 1/3 t. A1 is t, and A2 is 0. So any function in the form negative 1/3 t plus tx should work for all values of t. We can check that. Easiest thing to check here is to let t equal 3. If I take the transformation of negative 1 plus 3x, this gives me 2 times negative 1 plus 3 plus negative 3 times x, which is 1 minus 3x, which is negative 1 times 1 plus 3x, which is exactly what we started with, times negative 1, which is the eigenvalue. So that one checks out. Number 5 is basically the same problem, except for we do it with matrices instead of polynomials. So let's do that. All right, so we're given that the transformation of some 2 by 2 matrix is going to yield another 2 by 2 matrix, right? I have A minus C plus D, B plus D, negative 2A plus 2C minus 2D, and then 2B plus 2D. Okay, so just like the functions, we can build a matrix that we're going to take the eigenvalues of. We just use these as the rows. So you're going to get 1, 0, negative 1, 1, 0, 1, 0, 1, negative 2, 0, 2, negative 2, 0, 2, 0, 2. You can look at the structure of that a bit. It'll give you some hints as to what's going on there. If you find the eigenvalues of this, you get 0, 3, 0, 3. So fortunately for us, we only need 2 eigenvalues. So let's start with what happens when lambda is 0. All right, so let's let lambda 1 equal 0. Well, if I take 0 times any matrix, I get the 0 matrix, so that's easy. And I want that to be equal to A minus C plus D, B plus D, negative 2A plus 2C minus 2D, 2B plus 2D. All right, so the 4 equations here are really easy to see. It's A minus C plus D is 0, B plus D is 0, negative 2A plus 2C minus 2D is 0, 2B plus 2D is 0. So the augmented matrix here is just going to be 1, negative 1, 1. Sorry, there's a 0 for the B there. 1, 0, negative 1, 1, 0, 0, 1, 0, 1, 0, negative 2, 0, 1, negative 2, 0, 0, 2, 0, 2, 0. And when we Gauss-Jordan, we end up with 1, 0, negative 1, 1, 0, 0, 1, 0, 1, 0, and zeros everywhere else. All right, so this means I have 2 free variables here, okay? So A minus C plus D has to be 0, okay? And B plus D has to be 0, right? So it's really just the original 2 equations up here because these are not linearly independent. So let's let B and D be the independent variables, right? Or no, sorry, C and D are the independent variables. So A will be S minus T, B will be negative T, C comes out as S, D is T, right? We can play that out and make that all work. All right, so any matrix in the form S minus T, negative T, S, T is an eigenvector for the eigenvalue 0. This means if I perform the linear transformation on something, so let's let I don't know, let's let s equal 2 and let t equal 1. Doesn't matter what you pick for s and t. 2 minus 1 makes this 1. Negative 1, 2, and 1, right? So if I perform that, I should get 1 minus 2 plus 1, right? And then I should have negative 1 plus 1. And then I should have negative 4. Nope, negative 2, right? Because that's negative 2a. So negative 2 plus 4 minus 2. And then 2 minus 2 makes this whole thing 0, 0, 0, 0. Which means that if I take 0 times this matrix, I get back this. So the transformation here of any matrix of this form is going to be the same as multiplying the matrix by 0. So let's look at the eigenvalue 3. So I should be able to do something very similar. All right, so we're going to say the eigenvalue is now 3, which means if I take 3 times the matrix, I should get back a minus c plus d, b plus d, negative 2a plus 2c minus 2d, 2b plus 2d, right? So 3a is going to be a minus c plus d, 3b is going to be b plus d, 3c is equal to negative 2a plus 2c minus 2d. 3d is 2b plus 2d. Putting these in standard form, I'm going to get 2a plus c minus d is 0. 2b minus d is 0. 2a plus c plus 2d is 0, and then negative 2b plus d is 0. So the augmented matrix there is going to be 2, 0, 1, negative 1, 0, 0, 2, 0, negative 1, 0, 2, 0, 1, 2, 0, 0, negative 2, 0, 1, 0. We do Gauss-Jordan here, and we end up with 1, 0, 1 half 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, and then a bunch of zeros, right? All right, so this means that a plus 1 half c is 0, b has to be 0, and d has to be 0. So we can let a equal negative 1 half t, b be 0, c be t, d is 0. So any matrix A2 of the form negative 1 half t, 0, t, 0 should be an eigenvector corresponding to the eigenvalue 3. All right, so let's try this for t equals 2. So we're going to do the transformation on negative 1, 0, 2, 0. All right, if I do that, I should get negative 1 minus 2 plus 0, 0 plus 0, 2 plus 4 minus 0, and then 0 plus 0, right? So this comes out to be negative 3, 0, 6, 0, which is exactly 3 times the original matrix, which corresponds to the eigenvalue 3. All right, so spend some time with that. It's a complicated set. Make sure if you got questions, you're bringing them to the small group or the drop-in, or sending questions to me via email might be helpful. So there's eigenvectors and linear transformations. Thank you.